And good day to our lecturer. Today, we will like to present about design and MATLAB simulation of an amplifier. Our amplifier is band pass filter. Next. This is our group member, which is consists 6 students. Next. My name is Maisara Shafika binti Muhammad Nur Azman. I would like to present about our introduction. Bandpass filters are essential in modern technology, isolating specific frequency bands for various applications. In communication system, they enable channel selection and interference suppression, crucial for radios and mobile networks. In audio processing, they enhance sound quality in equalizer, microphones, and speakers. Medical devices like ECG and EEG machines use them to extract physiology signals, while radar, sonar, and ultrasonic imaging rely on them to reduce noise and impressive key frequencies. These filters come in different forms. Active filters using operational amplifier are precise and ideal for audio and biomedical use. Passive filters made of resistor, capacitor, and inductors are cost-effective for high frequency. Digital filters implemented through algorithm offer flexibility in application like software-defined radios. Next, I will pass to Koyu.
Hi, my name is Mohammad Shikoyu. So I would like to talk about pros and cons of band pass filter amplifier. We got two advantage and disadvantage. We go for the advantage first. We got the frequency isolations, filter and amplifies signal within a specific frequency range, improving the stability and performance of the control system by isolating desired frequency. Second one is tunable design. The passband can be adjusted by modifying resistor and capacitor value, making it adaptable to different control applications. Next, noise reductions emit high and low frequency noise outside the passband, ensuring clean signal and fed into controller. And last one is enhanced stability, help prevent instability caused by unwanted frequency component that can resonate with the control system. So, from the advantage, we got the provide significant advantage, including the frequency isolation, tunable design, noise reduction, and enhanced stability, making it a powerful tool for applications that require precise signal processing and improve system performance. So next one, you go to the disadvantage. First one is phase shift, introduce phase tag and phase lag or lead, especially near the edge of the passband, which may complicate the control system phase margin and stability. The next one, component variability, real world tolerance, and resistor and capacitor can lead to device change in performance. Third one, frequency dependence. The filter effectiveness is restricted to a specific frequency range, limiting its utility in system required broadband response. The last one is design complexity, required precise component selection and tuning to achieve the desired passband, increase design and teasing effort. So we got the advantage, challenge such as phase shift, component variable, and frequency dependence, which can impact its stability, accuracy, and versatility. So next one. So this circuit design which represent a band pass filter amplifier. So let me take a break down the design and functional of the circuit. So the main purpose of this circuit is twofold. The first one is the band pass filter and the second one is amplification. So by combining these two functions, this circuit is widely used in systems that require frequency selection, such as audio processing and communication device. So now let's look at the component of the circuit and how they contribute to its functional. So the first one, you got resistor R1 and C1. These two components form a high pass filter at input of circuit. So the high pass filter allows signal which are frequency higher than a specific. So the cutoff frequency of the high pass filter can be calculated using the formula FC 1 over 2 pi RC. If you calculate using by this formula, you got 3.54 Hertz. So it means that signal below 3.54 Hertz are significantly attenuated. So for example, it's a signal contain frequency of 1 Hertz, 10 Hertz, and 100 Hertz. Only 10 and 100 Hertz will pass through this stage, while 1 kilohertz, 1 Hertz will be blocked. But differently for this low pass filter, which is C2 and R2, why I say different? Because low pass filter allows signal with frequency lower than specific, while high pass filter allows signal with frequency higher than specific. So that's the difference between these two filters. For example, after you calculate using the same formula, you will get low pass filter 4.31 Hertz. So let's say the signal contains 1 Hertz, 5 Hertz, and 10 Hertz. Only 1 Hertz and 5 Hertz will pass through this stage, while 10 Hertz will be blocked. So the third one is operation amplifier, which is OM. This component serves two main functions. It's amplify the filter signal, ensuring its amplitude is sufficient for further processing. The next one, it works with the feedback network low pass filter to maintain the circuit band pass filter. So next one is key features of circuit, how it works. Let's go step by step through how the operations. So the first one is input signal, Vin. A signal contains a wide range of frequency is applied to input the circuit. The next one, high pass filter, which R1 is C1. The high pass filter will block low frequency component below the cutoff 3.54 Hertz. Low pass filter. So low pass filter will block high frequency component above the cutoff 5.31 Hertz. So after the wrap up, band pass filter. By these two combination, high and low pass filter, only frequency within range 3.54 Hertz to 5.3 Hertz are allowed to pipe this through. So next one is amplifier stage or M. Once the signal is filtered, the operation amplifier boosts in its amplitude. Next one, output V out. The output contain only the design frequency range amplified for further use. So next, we got band pass filter amplifier block diagram. So this represents a system level value. So the first one is input signal sources. It's typically a sine wave containing a mix of frequency. The second one is transfer function block. Combine this the high pass filter and low pass filter function into one. But the equation is here the equation to get the numerous and denominator. And the third one, amplify block. The filter signal is amplified by the gain factor of 10. And then the last one is output display. V out will be displayed at the monitor. So next.
Okay, so thank you, Koyu. My name is Muhammad Rami bin Muhammad Anwar. And so for the setting block diagram in Simulink, so how it works basically, if the input amplitude is V in, for example, is 1 volt, which we use 1 volt, the output after the gain will be V out equal to AV time V filtered, which mean here we put 10 gain, right? So which mean our expectation is from 1 volt to close to 10 volt. So that's our expectation for our circuit. So next. So for the parameter setup, as Koyu has explained to us, for the low phase and high phase, for the low cut off frequency and the high cut, which we use 3.554 Hz, and for the high cut we use 5.31 Hz, which change to angular frequency is 22.22 radian per second and also 33.33 radian per second, which means this is the level we expect our circuit to work in, which is around 3.54 Hz to 5.31 Hz. Next. So by using the Laplace equation, we get our numerator, which is 333.1.3 and 0, and denominator we get 1 to 55.3 740.55 and 740.74. This is will be our denominator. So next. So next for our transfer function, which uses the second order system, we get our transfer function, which is this is the result we get from our calculation. Next. So for the damping ratio, which we use the damping ratio formula. Our damping ratio, we use the denominator in the middle, which is 55.55, and the highest, which is 740.74. By doing the math, we get 1.021, which is one, which mean our damping ratio is 1, which is could be labeled as extremely damping. Next. So this is our MATLAB code, which shows the first code. The first code basically shows to get the purpose for the first code is to get the plot magnitude phase response and give a transfer function. And the second part is the second part of the code, which is next. The second part is to show the system time domain response cosine with the wave input in various frequencies. So next. So in this graph, as you can see, is the system response, which shows our input is 1 volt, and then our output, which different with depending on the frequency. Which, for example, in 1 hertz, we get around 4.14, and also for 3.4 hertz, we get around 5.83. Yeah, and you can also see next. You can also see for 4.33 and also 5.3 hertz, also the same is amplitude the voltage. Next. And also for the 10 hertz, it's also amplitude the voltage to 4.36, I think. So next. So in this magnitude versus frequency, as you can see, uh, it shows that it's going up and then go down, which means here the dot plot demonstrate that the system is stable with significant phase margin, and also exhibit peak gain at 21.8 radian per second, which means that's around the 21.8 radian per second is the peak for the system uh, before it gets unstable. Next. So for the phase versus frequency, uh, as you can see, uh, uh, is highlight the margin greater than zero instability, which mean here, as you can see here, it's going down, which mean some, for example, 63.9 usage take longer to to decrease the voltage, because it has extreme filtering need to be involved, for example. Next. So this is the result where we put side to side. As you can see, this is what we get. So next. So this is the pole zero map. As you can see from the pole zero map, our zeros is 0, and our pole is negative 22.2 and also negative 33.3. Because both of of our pole is on the left side, this this shows that our system is stable. So next. Yeah, in this MATLAB simulation result, it shows here our zeros is 0, and pole is negative 33.3167 and negative 22.2333, which mean both are on the left side of the graph, which mean we successfully make our amplifier to be stable. Next. So from that, we use the second order equation to to calculate our magnitude and also phase after we do the derivation for the formula. Next. So as you can see, for the plot 1, for the magnitude we get 8.63, and for the phase we get 26.56. Next. For the plot 2 we get 15.35 dB, and for our phase is 77.6 degree. Next. And for plot 3 we get 15.54 dB, and our phase we get negative 86.1 degree. Next. And for the magnitude we get 15.33 dB, and for the phase we get negative 77.03 degree. And lastly, for our plot 5 we get 12.81 dB, and for our phase we get negative 132.95 degree. So next, for the result table, I will pass to to the next person.
Assalamualaikum. My name is Muhammad Kamazim, and today I will explain about the vote for each result. Okay. So let's start with 6.362 radian per second, which is approximate 1.01 hertz. At this frequency, the magnitude is 8.63 dB, indicating noticeable attenuation of the input signal. The phase shift is 26.56, showing a slight lag. The corresponding output voltage Vout is 2.7 volt. Since the frequency lies below the passband, the system acts as a high pass filter, attenuating low frequency signal and introducing some phase delay. This is typical behavior in the low frequency range of a high pass system. At 21.811 radian per second, or roughly 3.47 Hz, we observe a significant increase in magnitude to 15.35 dB, indicating strong signal amplification. The phase is 77.6 degree, showing a leading phase shift, and the output voltage rise to 5.8 volt. This frequency marks the system transition into the passband, where amplification of the signal become more prominent as the input signal frequency match the system resonant characteristic. The output voltage increase significantly. This behavior is crucial for understanding the system optimal operating range. Next, at 29.1696 radian per second, or approximately 4.64 Hz, the magnitude reached its peak value 15.54 dB, representing the highest level of signal amplification. The phase shift to negative 86.11 degree, indicating a noticeable delay, and the output voltage reached its maximum at 5.9 volt. This frequency represents the center of the passband, where the system operates at peak efficiency. It is here that the system provides maximum gain, which is critical for application requiring strong signal output. However, the significant phase lag must be considered in time-sensitive system. Moving on to 34.4409 radian per second, or around 5.48 Hz, the magnitude slightly decreased to 15.33 dB, reflecting a slight reduction in gain. The phase is now negative 7.03 degree, and the output voltage decreased slightly to 5.8 volt. This frequency lies near to edge of the passband, where the system amplification starts to decline, and the phase lag continues grow. This marks the point where the system begins transitioning into the stop band, losing its ability to amplifying higher frequency signal effectively. Finally, at 63.3291 radian per second, of approximately 10.08 Hz, the magnitude drops significantly to 12.85 dB, indicating strong attenuation. The phase is negative 132.95 degree, showing substantial lag and the output voltage fall to 4.3 volt. This frequency lies into stop band where high frequency signals are heavily attenuated and the low pass filtering effect become dominant. The system is no longer effective at amplifying signal and exhibit considerable delay. So that's all from me. I will pass to the next person.
Okay, thank you, Akram. Okay, my name is Muhammad Rizwan. I will present about analysis. Okay, first, passband behavior. Frequencies between 21.811 radian per second and 54.4409 radian per second exhibit strong amplification. At 29.1696 radian per second. From our observation, strong amplification occur within this range. Okay, for the second, high pass filtering below the passband 6.362 radian per second, the circuit attenuates the signal with minimal gain and slight lagging phase. Okay, for the third one, low pass filtering above the passband 63.3291 radian per second, attenuation increase. The phase lag becomes significant. For the last pass transition, the phase shift from leading positive 77.6 degree to lagging negative 132.95 degree. The frequency move from the lower edge of the passband to the beyond edge. Okay, that's all for me. I will pass to the Hakim.
Thank you, Sazwan. My name is Ahmad Zul Hakim bin Ahmad Zaki, and I will talk about conclusion. In conclusion, our project successfully demonstrate the design and simulation of a bandpass filter amplifier using MATLAB. So we can see through the three main key characteristics, which is first is frequency selectivity, which is the circuit effectively amplify signal within the passband defined by low and high cutoff frequency while alternating frequency outside this range. This ensure precise control of frequency component. Second is phase response. The phase shift transition smoothly across the passband, providing insight into the system response to input signal, which is crucial for stability in control system. Then the last is component justification, which is the chosen resistor and capacitor value, like R1 equal to 3 kilo ohm, R2 equal to 2 kilo ohm, and C1 equal to C2 equal to 15 millifarad. Strike a balance between the desired cutoff frequency and practical component availability, ensuring efficiency and reliable operation. So overall, this amplifier design highlight the importance of signal conditioning in control system, reinforcing key principle of frequency selective amplifier management. So that's all from us. Thank you for your attention.
Okay, thank you. That's all from us. Thank you for listening.